Okay, so our last talk of the day and of the school is Mauricio Lasco of the Mathematics Department here at Universidad de los Andes, and he will talk to us about graph learning, robust optimization, and the Wasserstein nuclear method.
That's right. All right, so first of all, I want to begin thanking the organizers for a very enjoyable conference and the speakers for the very good talks, and all of you to be here at this time after a whole week. So I will try to, since it's the last talk and we are all tired, I'll try to go slowly. If there are any questions, please feel free to stop me and I'll try to answer them. I will do the weird thing of having slides in Spanish and giving the talk in English so as to reach the largest possible audience and as to reuse some of my slides. So feel free to ask questions in either language. We figured something out. Okay, so what I want to talk about today is joint work with my former student Daniel Derroux, and is about learning on graphs, robust optimization, and the nuclear Wasserstein metric. So let me just give you this is the densest slide of the talk. I will describe what the outline is going to be. So I'm going to begin by giving you some summary about graphs and random graphs. And then I will discuss our main problem, which is the question of how to build deterministic summaries of random graphs from samples. So I will be working in the same learning setting we have discussed during the school, but the kind of problems I will ask are slightly different, and so I will try to explain what is it that we want to do. Then I will discuss some preliminaries which are needed to be able to describe the answers that we were able to provide. About robust optimization and the Wasserstein distance. This concept in particular, Wasserstein distance, I think is going to be of interest to many people in the audience, if for no reason, because it was actually physically motivated. It's a distance between probability distribution that is motivated in physics. And finally, we'll discuss our results. Our results are basically three. We devised a new algorithm using the Wasserstein spectral norm to solving this problem. Second, we proved some theorems guaranteeing that the algorithm behaves as we wanted, namely that it's capable of learning very quickly in an exact manner. This is what we proved. And finally, I'll show you the performance of the algorithm in a few numerical simulations, but these are more academic examples rather than actual real examples of interest to practical applications. Okay, so let's begin with graphs. So what's a graph? Throughout the talk, what's the formal definition of graph? A graph consists of a finite set of vertices and a collection of edges, which is just a subset of vertices times vertices. However, in practice, the way one thinks of a graph is through these two completely equivalent representations. The one on the left, which is a graph is just a bunch of dots and edges between them. But you can also think of a graph as a special kind of matrix, the adjacency matrix of the graph. Okay? So the matrix will have as many columns and rows as there are vertices, and I have a 1 here because there is an edge between vertex 1 and vertex 2, and this 1 is in position 1, 2. Yeah, and I will have a 0 in position 1, 3 because there is nothing between vertex 1 and vertex 3. So throughout the talk, I will equivalently speak about graphs and 0-1 matrices with this correspondence. And now let's think about why are graphs interesting. Well, they are a fundamental mathematical structure which simply appears everywhere. I'll give you 3 silly examples where the point is more explaining the different magnitudes of the graphs one might be interested in discussing. So first graph, the votes of congressmen. So let's suppose that the vertices are congressmen and we connect 2 Colombian congressmen with an edge if they have voted in the same way on a given fixed project. So you choose a project you're interested in and you color the graph that way, and this is a small graph. It has 268 vertices. Now, a slightly larger graph comes from biology. There are these protein-protein interaction networks. So vertices are the proteins of an organism, and we connect 2 of these vertices if they interact in some of the organism's biological processes. So I looked online, and for Helicobacter pylori, as of 2014, which is where the year of which I found this article, they knew 1,515 proteins, and only 3,004 edges. So it's a graph with 1,515 vertices and with rather few edges as compared to the total possible. Yeah, the number of edges could be like the square of the vertices, and this is much, much less. So it's a sparse graph with around 1,000 vertices. And then the third example is the so-called friends of Facebook, in which we have graphs with 2,230 million vertices, which probably half are false, but that's besides the point. Is really to get you a sense of how large are the graphs we might be interested in trying to understand. Now, if you think of any of these examples, these graphs change over time. Trying to model in detail the ways in which these graphs change is completely out of reach to any kind of modeling technique. So what people do normally is they refer to the formalism of random graphs. So what kind of mathematical structure serves to model the behavior of a complex graph that's evolving? Typically people use what are called random graphs. So what's a random graph? Formally, a random graph with vertices 1 to n is a random variable that takes values in the set of such graphs. And the important thing of thinking about it as a random graph is that instead of knowing whether a property holds or not in our graph, what we are able to know is what's the probability that our graph satisfies it. And so since these are the only questions we can ask from the model, fitting a probabilistic model to a real structure is easier in the sense that all we need is that it reflects the statistical properties of the object we want to observe. Okay, so this is why random graphs are important and random graph modeling is interesting. So now, just to make this more concrete, let me give you one concrete example of a random graph, which is the stochastic block model. Is used in many different circumstances. So it's a useful thing to know. So I'm going to describe for you how do you construct samples of a stochastic block model. Okay? So to do that, you have to give me, so we are thinking of graphs with a fixed number of vertices, always n. So you have to give me a partition of these n vertices into two disjoint sets, which we will call clusters. Let's suppose the blue points and the red points. I split the vertices into two classes, C1 and C2. And you also have to give me real numbers, P1, P2, and Q, where Q is less than 1/2 and P1 and P2 are strictly more than 1/2. And then with this information, I can create my random graph through the following procedure. I will produce an instance of the graph, putting edges in an independent manner, where the probability of connecting vertices I and j is given by this formula. So I will use probability P1 if I and j both belong to the first cluster. I'll use probability P2 if I and j both belong to the second cluster, and edges that connect one cluster to the other will be put in with probability Q. And I just do this independently across all edges. Okay, so let me give you an example of what kinds of graphs can I produce like this. So here I have 4 realization of a random graph on how many vertices? On 9 vertices. So you give me the blue vertices on top and the red vertices below, and now I add the edges according to the probabilities that are drawn up there. Okay, and now if I move the probabilities a little, I obtain this sample. So they were different, right? I mean, because Q has increased, now it's much easier for the graph to admit connections between the clusters. Okay, so it really does matter what kind of probability distribution do I set up, because the graphs look very different. So we have either that or that. However, typically, when we are thinking about the problem of graph learning, what we have is just a sample like this. You're given these 4 graphs and you have no idea how they were generated. Okay, and the question is about learning. How do you find or how do you learn properties or statistical properties of a random graph from a sample B1 up to Bn of it? Does it make sense, the question, at least at the moment? So imagine you have, I don't know, the graph of Facebook at 4 different instances in time, and you want to try to ask something about the graph. And the question is, how do you do that? So, yes?
Which thing you...
That's the next slide. So what kinds of things does one might want to ask? That's a very reasonable question. So what I would like to do is I want to try to find deterministic summaries of graphs. What does that mean? This means, so let me read the definition. A deterministic summary of a random graph, calligraphic G, is a normal graph A star. This one is deterministic, no longer random, that has the property that differs with G in the smallest possible number of edges on average. Okay, so what I'm trying to say is, the problem I want to solve is how do you find a deterministic summary of a random graph from an independent sample? Maybe a concrete example might make this definition more palatable. This is what I want to do. You're given these 4 samples of the graph, and what you would like to do is produce this picture. That somehow a computer realizes that there were in fact 2 clusters, which are these red guys and these green guys, and that the structure is that they were all connected together and these guys were all connected together. So something that will discover from the samples the clusters. This is the earliest kind of learning that one might want to do, and what I will be focused on here. Yes?
So can you not learn a distribution over the matrices, the adjacency matrices? And
I could, and one could try to get a sense of the distribution, and one could use things like a restricted Boltzmann machine to do this. But what I want to do now is basically the problem of the so-called community detection, which is given a bunch of samples of graphs, try to find the communities, the complete subgraphs that really control the underlying structure of the graph. Okay? I like this learning problem for many reasons. One is because I have a truth to compare my algorithms to. Okay, so if I know so secretly in my pocket I know that I made this with the stochastic block model, then I put them into my algorithm and I can check whether the answers I get are true or not, and then I can hope to prove theorems. But one could ask all kinds of questions. Yeah, the most general one is precisely the one you ask: can you actually recover the distribution? Yeah. Okay, so this is it. And now, since we are now focused on the problem of doing community detection or finding deterministic summaries, let's try to make this as precise as possible. So I'm going to now frame this as an optimization problem, a classical optimization problem, and then we will make it into learning and solve it. So again, okay, our definition of deterministic summary that I had in the previous slide, and now I'm going to describe mathematically what is this thing of finding a deterministic summary. The problem is one of optimization. I want to find the matrix A star with entries in 0, 1 that minimizes this risk function, which is defined as the expected value when B has a distribution of G of the L1 norm of the difference between A and B. Okay, let me just clarify for a moment what is this L1 norm. So the L1 norm of a matrix is simply the sum of the absolute values of all its entries. So this A minus B1 is, if you have that A is the adjacency matrix of a graph and B is the adjacency matrix of another graph, this difference, all it's measuring is how many edges do they differ in. Okay, how many edges are there in A that are not in B, plus how many edges are there in B that are not in A. So this is just formalizing in an obvious way. What does it mean to take a deterministic summary? It's just finding an A which differs on average from G in a smallest quantity, because I'm trying to minimize this function. Okay? However, and of course, if I knew the distribution of G, this would be just a classical optimization problem. I compute my expected value and then minimize in some way. Yes?
A is discrete, right? Like
A has to be discrete, yeah. A in principle runs in the set of all 0, 1 matrices, which is 2 to the n squared elements. So it's some finite set. And I want to do this. But it's not an optimization problem, but a learning problem, because the only thing that I have in the world to try to do this is the sample of G. I don't really know the distribution of G, but all I know is the sample. So what do we do? Okay, and more precisely what we are trying to do is find an estimator, A bar, depending on the samples, of the true cluster structure, A star. Is the question clear so far? Some of you guys are looking at me and giving me very little information. So is this clear? Is the question clear, what we are trying to do? Okay, so just we are trying to minimize this expected value, but the tricky thing is that this is done from samples. Okay, so how do you do that? So the first and most naive idea is just take the empirical measure. Define mu bar to be the empirical measure, so use your samples, and imagine that your estimation from your samples is good enough so that if instead of thinking that B is distributed according to G, you think that your samples are the true thing, and just try to solve your estimator for the risk. Okay, this is the most naive thing, the first thing that one would do. And if you do that, The advantage is that what you obtain is a linear optimization problem. And if you think of the solution of this linear optimization problem, what we are doing is something very simple. You just take your samples, look at each edge, and count in how many of the samples does the edge appear, and in how many of the samples does the edge not appear. And if it's bigger than 1/2, you put it. If it's less than 1/2, you don't. So that's the naivest possible solution. And this naivest possible solution has a few advantages. So the first one is that it's very simple. So you can run this and it's trivial and you can do it in an infinite graph. In the Facebook graph you can do this. And the other advantage is that it leads to a consistent algorithm in the sense that as the number of samples grows, you are guaranteed to eventually reach the truth, to eventually reach the correct A star. However, this idea has a huge problem. The problem is that the empirical measure given by our samples and the true measure G could be extremely far away if your sample size is small. Yeah? And this makes our minimizer, the one that we computed, to be very far from the truth. This is a way of mathematizing the concept of overfitting. We are believing our samples too much, and we do this crazy optimization, and we obtain a result that's unrelated with the truth. So let's do it in a picture, because that always helps. You have This is a space that later we'll talk about what space is, but this dot is the real probability distribution. This dot is the empirical measure. We are trying to minimize this risk, which since it's according to the empirical measure is called the empirical risk. And then as the number of samples grows, mu does approach G, and we can understand the rates at which this happens, but it might be that they are too far. So what do we do? This is our first idea, but maybe we are only here. We only have a few samples and these two are too far and we cannot do anything. So then what alternative do we have? Is there anything we can do? So one alternative is the following. Instead of thinking that mu is just a single point given by the empirical measure, I'm going to allow myself a ball of distributions around the empirical measure. Okay? And I'm going to replace my risk function, which used to be just the expected value of B with the empirical measure, to be the supremum in this ball. Okay? I'm not looking only at this distribution, but at any distribution in the ball, and I want to let my risk be the worst choice in here. I want to be more defensive. I want to be more, actually the right term is robust. And I'm going to try to solve this so-called robust risk. And what advantage does this have? Well, the advantage you can see in a picture right away. As the number of samples grows, mu does approach G, but then eventually it happens that your ball contains G. And at that moment, the robust risk you computed is an upper bound on the true risk. Okay? And then trying to minimize that will guarantee that what you get is a reasonable choice, or has less risk than what you actually computed, even in the true distribution, even if you don't know that true distribution. Okay, so this change is an interesting. I mean, this could be this is clearly a useful idea in the sense that your computation will give you a true upper bound on the risk of the real distribution, at least if the ball is sufficiently large. So that's what we will try to do. We are going to find a bar minimizing the empirical risk, the robust, not empirical, this should say minimizing the robust risk, which is defined like this. So if you want to take something out of this talk, is this idea. Replace empirical risk by robust risk, and this will lead you to good things. Now, in order to do this, we have a few problems to address. The first one is, how do I measure distances in the space of probability distributions? And the second is, how the hell do I do this optimization, since this picture is in fact in an infinite dimensional space? Yeah, I draw it in 2 dimensions because I don't have much choice on the slide, but it's really infinite dimensional. Yeah, the space of probability distributions on anything, on like a little 2-dimensional box, is infinite dimensional. Imagine just a bunch of deltas moving. Each of them is independent, and so of course it's infinite dimensional. So we have to address these two questions. Yes, of course.
It's a little bit related, but so if you change the norm, like to the L2 norm, can you map this to a quadratic and constrained optimization problem?
So I don't even have an L2 norm in the space of probability distributions. I could if I maybe chose densities and maybe do only distributions that are that have densities with respect to some Lebesgue measure, and one could do that. But even then, it's infinite dimensional. So
no, but I think it's the other norm.
Yeah,
the norm in the distance from the matrix.
Yeah.
Then, I see what you're saying. Yeah. Here, you don't want to do one norm but two norms. Yeah. You could. So I will prove theorems that you can do it with this norm, but it's possible to do some things with other norms. I don't wanna say just yet whether with L2 you could always do it, because okay. Let me show you the kinds of results we have proven, and then I'll tell you which ones generalize to that setting and which ones I don't know.
So
yes.
I understand the infinite dimensional concept.
So, okay, so what is the dimension of something? Okay, let's suppose that you have 10 points walking in this plane.
Yes.
Yeah? How many dimensions do you need to specify the positions of these 10 points? Well, each point has 2 coordinates, and since I have 10 points, I need 20 dimensions. Yeah, and they are independent because I can move the points in any direction I want. Now, allow yourself to, instead of 10 points, 20 points, 30 points, 60 points, 40 points, 80 points, and then it's clear that the space of probability distributions is infinite dimensional.
I would call it infinite. I mean, imagine that I have n particles in a cubic box. I would say that they are in 3D, but I have 3 to the n, like degrees of freedom. But yeah,
that's right.
3D.
No, so if you have n particles in a box, you have 3n degrees of freedom, because each of them has x, y, and z.
That's what I'm saying.
So that gives you
3n degrees of freedom.
That's right, because you're taking n particles.
But I don't have 3n dimensions.
No, you do have 3n dimensions for sure, because if you ask yourself, how many coordinates do I need to describe the position of n particles in 3-dimensional space? I need 3n real numbers. Therefore, you need 3n dimensions. That's
Okay, because
Say again?
No,
physical
I think
dimension.
I get your point, because the probability distribution is I mean, you can think of it as a probability distribution of matrices with 1-0 entries, right? You know, n by n matrices with 1-0 entries.
Yeah.
So the number of dimensions is.
No, but we have to not confuse the space in which these points live and the dimension of the configuration space of a set of points. The two are very different. So I agree that matrices, each matrix is specified by n squared numbers, that's for sure. But if I have a collection of matrices, this collection of matrices can move in n squared times the number of points I have. Yeah, this is so it's in that sense, yeah. And if you think of probability distributions, when you look at arbitrary probability distributions, you can have deltas supported in as many points as you want. So in that sense, it's infinite dimensional. Okay. Okay, so now let us talk for a moment about how do you measure distance between probability distributions. Okay. The Wasserstein metric is a special kind of distance between probability distributions, also called earth mover's distance, and is defined, it was coined by physicists, and is basically the smallest amount of work that you need to transform one distribution into the other. Okay, so let me show you a concrete example, because it's the best way to explain these things. Imagine that you have this probability distribution and this probability distribution in the same space. The space is this line. Okay, so we have 1 plus 4, 5 plus 2. I have 7 boxes, and here I have another 7 boxes, but they are arranged in a different way. And I want to know how much energy do I need to move from this configuration to that one. And the answer, so energy, I mean work. So like how much mass times distance do I need to do this? So the key point is to understand how am I going to move from this distribution to that one. And I have many possible choices. Let me show you one choice, and that might make things clearer. So I'm taking these 2 boxes, and I'm going to put one of them here and the other one there. I'm going to take these 4 boxes, and I'm going to split them like this. And I'm going to take this box, and I'm going to put it here. Okay, so this transportation plan is encoded by this matrix. I have 1/7 here, 0, 1/7, because I have 1, 0, 1. Okay, so the space of transportation plans between the two distributions is really the space of matrices with non-negative entries that sum to 1, yeah, which looks suspiciously like a probability distribution in the product space. And that's in fact what happens in general. If I have 2 measures, anything, not really discrete ones like this one, but just 2 measures, nu1 and nu2, the space of transportation plans between them is precisely the collection of probability distributions in the product whose marginals coincide with nu1 and nu2, just like in the previous picture. that we saw. Okay, and then I define the Wasserstein metric associated to a norm in K. So there are many norms in play in this talk, unfortunately. There is norm 1, which is the one that I'm using to define my risk. There is this norm that I'm going to use to define the Wasserstein metric, and there's the Wasserstein. So what's the Wasserstein? The Wasserstein is the smallest amount of work that you need to go from one distribution to the other. Okay, and this turns out to be a distance in the space of probability distributions. This work that you're measuring is really a nice concept of distance. Does this make sense?
What do you mean?
What is K again?
K is, I'm sorry, K is the name of the space where my distributions live. Okay, I should have said that in the past. Yeah, K can be anything, it's just some compact set in general. Yeah.
So work for you is just a number of boxes that you need to distribute.
No, the distance is important. So if I use this transportation plan, for instance, this box means that I have moved something from this point to wherever this guy is in the metric space. So the distance between these two, this distance I multiply by this mass and I sum everywhere.
So there's like an implicit sense of distance.
No, not implicit, very explicit. Yeah, I have chosen a norm in K with respect to which I will measure that distance. Okay. And then with respect to this distance, I have a concept of work, and I can look at the minimum work between two distributions. But this is very important. Your question is very good. So
computationally invariant or anything?
No, not at all. Exactly. You can choose a distance function, anything you want. There could be parts of the space where it's much harder to move and parts where it's not, and you can code that according to the metric you choose.
So X and Y, are they probability distribution or are they matrices?
So they are always probability distributions, that's right. Yeah, X and Y are probability distributions.
What's the definition of this infimum norm?
Of this infimum norm? So X and Y, okay. So X is a random variable that takes values on K. Y is a random variable that takes values on K. X minus Y is something you can take the norm of. Okay, and then you can take the expected value of that norm, where I'm thinking that the pair XY is distributed according to pi. Okay, so all I'm saying is, in order to find the Wasserstein distance between this distribution and that one, you need to look at all possible transportation plans and choose the one that has the least work. That's all that these definitions are doing. Okay. All right. So now with the previous definition, we can really make this into a precise statement. Given a sample B1 up to Bn, we define the empirical measure mu and define our estimator as a minimizer of this in where our ambiguity set, the green ball that I had a few slides ago, is defined in the Wasserstein metric. And then once we make this precise, we can ask, how do you actually solve for a bar? How do you find your estimator? And second, what properties does this estimator have?
That's why I'm confused.
Yes.
B from 1 to n, as far as I understand, they are kind of samples of some configuration of your graph.
Yes, they are samples of the graph, that's right.
And now the metric that you use to do the optimization is this supremum of the expectation value of those sample of A minus B.
That's right. Yeah. Mm-hmm.
But when you say that B is defining the metric of in this Wasserstein metric, this is where I'm lost.
So A and B are random variables taking values in the space of matrices, yeah? And so I can ask what's the expected value of this difference, because they are random variables. And then I want to not look at this expected value under the empirical measure, but in the worst measure in a ball.
Yes.
Okay, so that's where the Wasserstein metric enters. I'm taking the supremum, I'm taking the worst risk in all distributions in that ball.
Oh, okay.
Make sense? Just like I said I was going to do. Okay. So I said, okay, we're going to try to look in this ball and take the worst, the worst random variable. That's what we are going to do. That's what we are doing. Now, the ball before was just a green picture, and now it's something specific. It's a ball in the Wasserstein metric defined by another norm in the space. Okay, so now we can go to results. So if we measure the distance between probabilities using the Wasserstein metric associated to the spectral norm between matrices, so now I have chosen a specific norm between matrices, the so-called spectral norm, which is the largest singular value, then the following statements are true. First, A bar can be computed as the optimum of a semi-definite programming problem. Okay, so not only is now finite dimensional and convex, but it's something that you can really solve in practice with a computer. This is a non-trivial theorem. It involves results of Esfahani and Khan that are recent about tractability of Rost optimization, and it uses results of Boyd, Faisal, and Parillo about representability of norms with spectrahedra. But it's true. It's something that it gives us a mechanism to find your estimator A bar. And second, we were able to prove that A bar gives us consistent estimates of A star in the sense that there is a radius delta of n, so depending upon how many samples do you have, you're going to need to choose the radius of your ball differently as n goes to infinity. Now, okay, this theorem is true, but since I didn't explain anything of how I got it, this might sound like esoteric, so the next slide might help you to try to figure out what is it really that we did. This should not be a theorem, it's just a lemma. We proved that this quantity is bounded above by this other quantity, and it's through this other quantity that we really do the optimization. So if you are lost or something, you can ignore some of the stuff that I said earlier and just focus on this quantity so that I can really explain what is it that what does the algorithm that we do does. Okay, so my samples are called BI, so my samples appear here, and what I try to do is just minimize this function. So what does this function do? This function contains the empirical risk, which is this first term, and it involves also this regularized term, yeah, which is delta, where delta is the radius of the ball, times this regularization factor, which is a very specific regularization factor. Is of the form 2a minus 1 transpose, and is done in a special norm, in the norm that is dual to the spectral norm, in the nuclear norm. Okay, that's the sum of the singular values. So if you take a matrix, there is a norm called the nuclear norm, which is the sum of its singular values, and that's the metric, the norm I want to choose for regularization. Okay, and we proved that this process, this optimization problem, which is obviously a convex finite dimensional optimization problem, can be solved with semi-definite programming. Okay, so what I'm saying is this idea of the Wasserstein metric is a way of understanding where do regularizers come from. Yeah, in many of the talks that we heard this week, the coefficient in front of the regularizer was called a hyperparameter. It's just something you take out of your pocket. And what I'm saying is there is a real interpretation for what this hyperparameter means. It's just the radius of this Wasserstein ball. And that's quite useful. And then okay, when you represent your problem in this way, you can actually solve it. And so let me show you some simple computer examples of what you can do. So we took a graph with like 50 vertices, and I'm going to see, okay, so yeah, let me describe more precisely what is this experiment. So I have a graph with 50 vertices that I have sampled according to the stochastic block model. So since I know the cluster distribution when creating the samples, I of course don't give this information to my algorithm. I just put the samples in the algorithm and see what the algorithm produces. But since I know the true real thing, I can compare and I can see how big is the error that I obtain. And this error is exactly what this picture is showing you. Okay? So, and this factor over here is the radius of the ball, okay? So when the radius of the ball is 0, when I am doing only empirical risk minimization, this very naive idea of just using the samples, my error is huge, okay? I am getting an error that's like on the order of 500. And now as the radius of the ball starts growing, the error starts decreasing until something kind of miraculous happens, which is that we find one small spot where the error is actually 0. The continuous optimization problem produces a discrete optimum, and this discrete optimum is in fact the true result. And then as the radius of the ball keeps growing, then we are just adding too many distributions, and then it becomes noisy, and then it becomes junk as the radius grows a lot. Okay, so this is the kind of behavior that you see in the algorithm. The error decreases. Then, at least in this example, it becomes 0, and then it again increases. See.
Error here is the number of mismatches?
Yes, exactly. Error is number of mismatches. So, since the optimum of my continuous optimization problem is a matrix with entries that are real numbers between 0 and 1, it doesn't really have to be an integer, yeah? Because the continuous optimization gives me something that has 0.5, 0.7 in the entries. And so I do the L1 norm of that minus the true distribution, and that's what I'm plotting. Okay, so now let's look at the level of graphs. How does this same picture look like? I want to try to understand what are the graphs that I recover. So when delta is very small, I recover nothing. This is bad because so there were supposed to be orange edges, and these are very important. Okay, okay. So the most interesting ones or the most important are the ones that are in this like ugly green in the middle. So the true graph has two cluster sets, this one and that one, and my original recovery is a matrix that has values between 0 and 1. And I plot the edges in different color according to the weights. So basically everything is in this ugly green. And now let's see how do the recovered graphs look like as the delta increases. So now it's thinking, well, I believe that in this area, all the edges should be there because the weight is bigger than 0.6. I believe that in this green area, none of these edges should be there because the weight is less than 0.4. And there are a bunch of orange edges, the ones in between, where the algorithm doesn't really know what to do with them. And now we continue, and we see, okay, there are still orange edges where it's confused, but now it's kind of clear that green maybe should die and gray seems to be capturing the right cluster structure. We continue, and now this becomes much more pronounced. As delta grows, then it really sees, okay, I think that this is the right picture, and then as delta grows, it finds exactly the right cluster structure. There's a point in which it just realizes that it's exactly this, what it has to be, and then as delta keeps growing again, it gets confused, and at the end you get junk again. So this recovery really behaves like this. Okay.
I miss what is weight?
Sorry?
What do you call weight?
Okay, so when you run this continuous optimization problem, what the output of this optimization problem is a matrix, yeah?
Yes.
And the matrix has entries that are real numbers between 0 and 1.
Yes.
I call the value of that entry the weight. Okay, so if the weight is close to 0, then I draw it in green. If the weight is close to 1, I draw it in gray. And if the weight is kind of in between, I draw it in orange. Okay?
Then I missed it because in the beginning when you were doing the mapping from the graph to the matrices, you had just what is your 0, 1.
You're right. The thing is, the answer, so the answer of the continuous optimization problem is not for all choices of delta a graph. In general, it's just some continuous thing. And then we prove as a theorem that when the delta is just right, it turns out to have entries that are only the numbers 0 or 1, where it actually becomes a true graph, which is what you see here. Precisely at that point. You see, here it's really a graph. Here these are all ones, and these are all ones, and in between there are all zeros. But in the rest, the result is a matrix with entries, and I have no other way of drawing it that is more didactic than just coloring the edges. But this is what's going on. It's a continuous optimization problem, which with the right parameters has a discrete optimum. Does it make sense? Okay. Now, okay, so the next thing that one can do is what happens if I use different metrics. And it turns out that with the L2 metric, it's junk. You never learn anything. The Wasserstein metric associated to the L2 norm is just very, very bad. The algorithm doesn't learn. If I use the L1 norm, which is just linear optimization, then all I learn is this exact, the naive algorithm we had at the beginning, basically counting edges and seeing which is better and seeing which ones occur with probability more than a half and drawing those. This is all I can get, and delta does not make any difference. But compare this with the spectral norm. The spectral norm has, with very, very few samples, you learn exactly, as opposed to what you normally do when you take averages. So you really should try to dump this idea of just using the empirical thing. How much time do I have? Is it like 3 minutes or something? I'm close. Okay. Alonso, yes.
So what's the intuition behind the fact that the spectral norm is actually, how
Oh, so this is what we proved. That's the next thing. So we were able to prove that the spectral norm works, and the reason it has to do with the fact that the subdifferential of the spectral norm contains enough transportation matrices. So we proved it, but I mean, it's really, we used in a very delicate and focused manner very special properties of the spectral norm that are simply not true for any other. But it has to do with transportation matrices. I can show you, but it's hard to really summarize the reason during a talk, let's say. Okay, so the theorem that we proved is that in fact, when you run this optimization problem, if G comes from a stochastic block model, then there is a radius for which the probability that the estimator you obtain is not exactly the true result decreases exponentially with the number of samples. So not only does the algorithm learn, but it learns exponentially quickly and it makes no mistakes. You have absolute certainty of getting the exact optimum. So the algorithm learns the exact cluster structure in a few samples. And okay, that's it. Now, there's maybe one last slide of comments that I want to make, which is that the algorithm we propose uses semi-definite programming. And semi-definite programming is very powerful and very nice, but it has a huge problem, which is one of scalability. You cannot solve a semi-definite programming problem of more than matrices 200 by 200. It simply cannot be done with the usual, solvers such as MOSEC or some industrial solver. They are very accurate, but they were not designed to solve such large problems. And the reason is in part because they use interior point algorithms that are second order, and that's bad. So what we did with Daniel, and this is actually all of Daniel's idea, is that there exist first order methods called ADMM algorithms that are close to the kinds of gradient descent things that we saw during this week, that are just way better. And using them, using an industrial solver, we could use our algorithm for graphs with 40 vertices. That is really not so interesting. But with our version of the algorithm, we can go up to 10,000 vertices, which is nowhere near the Facebook graph, but is enough for applications in biology. So it's a range in which we think we have accomplished something, maybe not much. But the problem of scalability of these methods is really a serious limitation. We don't really know a way of doing this faster. And interestingly, it's not about algorithmic complexity. Semi-definite programming is in approximate polynomial time. So there might be much more clever algorithms that should be able to scale this beyond 10,000 vertices, but we just don't know them, and we have spoken with many people who don't seem to know them either. So that might be an interesting research direction. All right, this is what I wanted to tell you. Thanks.
Questions?
Andreas.
Semi-definite programming, the variables are semi-definite symmetric matrices.
Yes, that's right.
Your matrices are not definite.
No, not at all. No. So to rewrite this problem as a semi-definite programming problem is rather complicated. I mean, you need to take a much bigger space and just project. This is the usual, like Nesterov and Nemirovsky. They have all this theory of semi-definitely representable functions, which are functions such as their epigraph is a projection of a spectrahedron. The nuclear norm is one of these because of a result of Parrillo. So this is how we manage to do it. But it's rather complicated. It's not straightforward. I mean, no, it's really not so complicated either, to be precise. So the point is to say that a matrix has eigenvalues in a certain interval is the same thing as saying that A minus lambda I is positive semi-definite and A plus beta I is positive semi-definite. So for symmetric matrices, this is very easy to speak about the spectral norm. If your matrix is not symmetric, you need to construct an associated symmetric matrix where you can use that same trick, and that's easy with the Schur complement. That's how they actually do it.
But you are symmetric because you have undirected graphs.
Yeah, no, but not positive semi-definite. So what I want is to be able to make statements about the eigenvalues of general matrices, and to do that one can symmetrize and use obvious theorems about bounding eigenvalues of symmetric matrices. Yes.
There's a different way to find an optimal radio for the open bulb different case with a lot of radius in the sample?
So yeah, that's a very interesting question. So our theorem contains a formula for the right radius. It's delta of n, we have a closed formula. So that, however, this formula is valid for the stochastic block model. If you are trying to learn graphs that come from some random distribution, then you probably have to do some cross-validation or one of these typical tricks to get it.
Restricting or to you have a k times k in the space of probability.
Sorry, can you repeat the question? I missed the beginning.
Yeah, thank you. Excuse me. Can I take the space k to, you say, I need the space k times k.
Yes.
But can I choose k times L, for example?
So I use k times k because I'm interested in transports of a distribution from a space to itself. So the point is, these two distributions live in the same space, namely that line. And that's k, and so this is why I need to use k times k, right? Because, but in principle, I mean, you could think of transporting from k to L, but then you would need a kind of concept of distance between points in k and points in L. And then you could define some generalization of the Wasserstein metric. I don't see any reason why you cannot do that. Yeah. It would no longer be a metric, but it would be some kind of divergence concept between distributions in two spaces. That's something reasonable. But you need a map in between. That's what I'm saying.
One question.
Are there any more questions?
I had one
Alonso.
quick question. I don't know, have you thought of, sort of like translate or, like building some sort of generative model out of this? I mean, like once you get your, what do you call this matrix?
This deterministic summary or something?
The deterministic summary. I mean, could you use it to create new samples of,
So for instance, that's a very interesting question. So in the case of the stochastic block model, if I do the deterministic summary, I will have understood the cluster structure. Now, with that information, inferring the probabilities becomes very easy. So one could use that in the case of the stochastic block model to like reverse engineer the model just from samples, and it would be very, very fast. However, if your generative mechanism is very different, I don't know, like a small world network or one of these many other, then no, the deterministic summary will tell you so little compared to the space of possible district that might not be so useful.
Have you ever tried to use your graphs to query language examples?
No, so as I said, this is something that we just finished. So my student just finished, and now he went to Carnegie Mellon, so he's no longer going to keep working on this. And so with the project has become orphan. We just will publish it and then move on to something else. So we had time to prove these theoretical things, and of course to do many simulations that motivated the theorems. Yeah, there are theorems, but all of this is possible only because we made a lot of computer simulations, and the simulations taught us what was true, and then it's much easier to prove. But we did not think of real applications, like really let's focus on a collection of graphs we're interested. No, so this is something that can be done. So my student put his implementation in, it was made in Julia and is available in GitHub. So if you are interested in playing with this, please go ahead. That's a possibility. Yeah.
Okay. Well, let's thank our speaker again.
Thank you.
Okay, so we stay in the room, we wait for people from C to come down. People from C come down.
What is people from C?
From the other room.
Ah.
Okay. So there's a delay, so we'll see them in a second. Okay.